Okay, here's a quick review of lesson 1.2, continuity. So in order for a function to be continuous, the big thing we have to remember is that there are three conditions that have to be satisfied. So condition number one, f of c, whatever the number in question is, has to be defined. We have to be able to get an answer when we evaluate the function at c. The limit as x approaches that same number must exist, which means really the limit as x approaches c from the left must equal the limit as x approaches c from the right. And then finally, I wrote here number 1 equals number 2. In other words, f of c has to be the same as the limit as x approaches c. So those three conditions all have to be met in order for a function to be deemed continuous. Let's look a little further at a couple other examples here. We have this concept of removable versus non-removable discontinuities. So as it stands now, we have two discontinuities to worry about here. And I know that because in a rational function, if the denominator is 0 at any point, it means it's not continuous. However, we may or may not be able to remove them. So take a look. If I factor the bottom, x minus 3 and x plus 2, that at least allows me to see that I have discontinuities at x equals 3 and x equals negative 2. Now, which one of these is removable? Well, it all comes down to whether or not I can actually find the limit as x approaches either of those numbers. So let's take x equals 3. If I take the limit as x approaches 3 of this more rewritten form here, right? These happen to cancel. I have 1 over x minus 3. And when I go to plug 3 in, I get 1 over 0. And that's obviously impossible. So therefore, this is what we call a non-removable discontinuity. So it's discontinuous, but it's not removable. Now, x equals negative 2. If I take that exact same problem, go to find the limit as x approaches negative 2 of 1 over x minus 3, I actually do get a value here. I get negative 1/5. So what that means is that there must be some type of hole in this graph where the function's doing whatever it's doing up until that point, and we remove that discontinuity because we could find the limit of the function as x approaches negative 2. Let's look at a different example. What do we do with a piecewise function? Well, in a case like this can be a little tricky here because we have many pieces, and they're asking us to find the value of a and b that make the function continuous. So this is a little bit more difficult, but it really requires that we understand some of the things we talked about before, the conditions of continuity. So the first thing I have to know is that if anything's going to happen here, I see that there's two potential breakpoints, 0 and 4. So the first thing I'm going to do is I'm going to find the limit as t approaches 0 from the left. And I know that as t approaches 0 from the left, the answer would have to be 5. Meanwhile, as t approaches 0 from the right, I plug a 0 in here, I'm left with b minus 2a, right? So in that case, what do I know? I know that b minus 2a must equal 5 if this function is going to be continuous at 0, because the limit from the left has to equal the limit from the right. Now, meanwhile, I have this break at 4 as well. So let's take a look at what's going on here. The limit as t approaches 4 from the left, well, I plug a 4 in here, and I would get b minus 8a. And then the limit as t approaches 4 from the right would just simply be negative 3. So what do we learn? These two things have to be equal to each other. So b minus 8a must equal negative 3. Now what I have to do is I have to take these two pieces of information and I have to figure out how to solve that. So we're just going to use a little bit of algebra here. So we'll come over here, right? Let's suppose that I know b is equal to, from here, 5 plus 2a. Well, let's now come in here. Instead of a b, let's put 5 plus 2a minus 8a equals negative 3. So I got to play around here a little bit, simplify, and I get -8. So A is equal to 4/3. And now that I have that, I can go find B. B must equal, let's say, 5 plus 2 times 4/3. And that would be 5 plus 8/3, or 23 over 3. So it's a little bit ugly. The numbers aren't so nice. However, in order to find both A and B, we really have to hone in on finding those one-sided limits at these breakpoints here, and then using almost a system of equations to kind of finish it off. Okay, one final example. Let's look at the intermediate value theorem. So I have a picture here because I thought this would help a little bit. And when we use the intermediate value theorem, we have to understand what it's really asking us and what it's telling us. So it says if a function's continuous, then there's got to be some point on an interval where if you started at a certain place and you end at a different place, you had to pass all these other values in between. So here's an example. So suppose that this person here is 5 feet tall on her 13th birthday. Well, 1 year later, she's 5 feet 7. Well, what do we know? We know that growth is continuous. And so if you grew over that 1 year, at some point during that year, you were 5'1", 5'2", 5'3", 5'4½", 5'5 3/4", all these other numbers until you got up to 5'7". So in a question like this, let's say we put this on a specific interval. Let's say 0 to 1. Okay? So this question saying use the intermediate value theorem. We have a continuous function to find the value of m for when h of m is equal to 0. And we're going to stay on this interval. So really, the intermediate value theorem tells us what's supposed to happen, but it doesn't tell us how to do it. Well, here it kind of is saying we have to set this equal to 0, and we have to solve it. Now, this is going to require a calculator, so make sure you're in radian mode. I'll give you a minute. And let's just take 1 second, get your calculator, and go find that value. Okay, I have my calculator here, so I graphed it over the interval 0 to 1. I'm really just looking for the root, the 0. So I get 0.5635. So h of m will equal 0 when m is 0.563, and then you could even go a little bit further. So the IVT guarantees us that it will happen. It doesn't tell us how many times it's going to happen. It just guarantees that if we have a continuous function, something like this would have to happen. So I hope this helped.